Yeah, so good morning, everybody. Well, it's morning here, good afternoon or good evening, depending on where you are. So today I've got an update on HyperMesh Design Explorer coming for the 2024 release. So let's jump in. Okay, so here's kind of the agenda. As you can see, I just got two things to share generally. The first one is a fairly small, but I think interesting enhancement. And the second one is an entirely new and I think very exciting workflow inside of the Design Explorer. So though there's only two things, number two is I think is pretty exciting and quite a large and brand new enhancement. So those are the things I'd like to describe today. Let's start with first with just the one separate enhancement that I just want to mention, and I'll demonstrate for you in just a second. But this enhancement is the ability to extend existing designs of experiments in Design Explorer, and this is something that hadn't previously been available. It's of course, for those familiar, it's of course something that you could do all along in HyperStudy. It just hasn't been possible in Design Explorer until now. And I think it's been a bit of a pain point, so I'm happy to have this enhancement to describe and share. And basically, up until this point, if you've run designs of experiments in Design Explorer, and maybe you know that can be pretty time consuming. You generate a lot of data, you spend a lot of time, and for whatever reason, you don't have sufficient information, or you want more data or more data points in your DOE. You were kind of stuck with Design Explorer. You'd have to start over and just request more runs. So what's depicted on this slide on the sort of the top row there is just showing you've run a DOE, and maybe it's a small DOE in this case, but it could have been quite large. And in this case, you ran an 11-run DOE. The scatter plot just kind of depicts the data that you've generated, and maybe you're interested in this example in looking at some fit results or some predictive results, which is one reason you might want to run a DOE and study your design space. And you note that one of the responses of interest, the fit has poor quality, or maybe not the level of quality that you're comfortable with to make your predictive capabilities or predictive do your predictions. So yeah, in the past or up until now, you'd have to just, one option is you could just rerun that DOE, and just instead of asking for 11 runs, which is the default in this case, you could ask for 20 or 30 or 50 runs and then go from there. With the new enhancement as depicted on the bottom row, you have the ability to extend the DOE, and we'll create an extended DOE for you. You can choose how many additional runs you want to run. And then in this case, yeah, the scatter plot is just showing the additional data that's been generated. And now, for example, your quality of your fit has improved dramatically, and you're on your way. So let me just quickly show what that looks like. I mean, the demonstration I can do here is pretty similar to what was shown on the slide, but I'll just kind of show where things are and how they look. Okay, so we'll open. This is the same DOE that was shown in the in the slide. So it's this. You may have seen this before. It's just this side impact B-pillar example using Radios, and we've run a DOE with 3 design variables. And by default, for a MELS DOE, we're going to default to 11 runs. The user may have accepted the 11 runs and run and generated the output. Here's the summary for the 11 runs. Come to the trade-off table, and as was shown in the slide, we see that yeah, our fit quality for stress responsive interest is not very good, or at least it's not bad, but it's not sufficient that we're comfortable with the predicted results we might get from this. So all we have to do now is come back to Design Explorer, or the Design Explorer tab, right-click on our DOE, and we have a new option, Extend DOE, which just creates basically a child DOE from the first one, and then we can come and submit additional runs. Again, same number of design variables, so it's defaulting to 11, but we can add as many more as we want. We can add 20, 30, 50, and then we run, and then we'll see that it accounts for the first 11 runs, and it just picks up where it left off and continues to run the extended runs. So let me jump to the end here. We'll open so we don't have to watch that run in real time. We'll open one where I'd previously run and added some additional runs, open Results Explorer, and now we can see our table has been additionally populated with, in this case, I think I asked for 15 more runs or 16 more runs. And we'll come to the trade-off panel, and we can see, as was shown in the slide, that our fit quality has improved due to having more data to be used, more data points when the fit was created. So I think it's kind of a handy feature. You can extend DOEs, you can extend them, again and again. If that was not enough, or you want to generate more data, you can continue to extend DOEs beyond that. Yep. So that's the extend DOE function or feature. Let's jump back to the presentation, and now I want to talk about generative design. And as I mentioned, generative design is a brand new workflow, still within the Design Explorer ribbon, and you'll see in just a minute how that looks and how it's exposed. But it is basically a workflow where for design or concept creation, concept ideation, and it has a number of features that are summarized here. So we'll go into a little bit of explanation on each of those, give you a look at the workflow, and then kind of go in again, and I'll try and do a live demo to show you what it looks like. But basically, the generative design workflow it's an extension of Design Explorer. As I say, it's a brand new workflow, but it is really Design Explorer. So it looks and feels and operates in much the same way. Everything is very graphical and GUI assisted. So when you're setting up your generative design is just another type of exploration that we can do. So when you're setting up your generative design explorations, you'll set them up in very much the same way that you do everything else in Design Explorer, and I'll demonstrate that. But the point is, it's very graphics driven, very GUI assisted, very automated, and the setup and execution works just like Design Explorer. So as such, we leverage a lot of the existing tools of Design Explorer. So once you've run your generative design exploration, we have a summary page that again looks very much like existing Design Explorer. You get a summary of each of your runs. In this case, each run is a generated concept, and you'll get a summary of the attributes or what the attributes are of a particular concept. And we've had for a little while this preview image that you can see there on the summary table within our existing explorations. And it's useful, but we don't see necessarily a lot of variation from one run to the next in a typical DOE or optimization. I mean, there might be some shape changes if you have shape variables, but in this case, this is where we really start to leverage this preview, because as I said, each and every run is itself a new concept that's been generated. So pictorially or visually, they look very different potentially. So you can see a preview of what each concept looks like. From the summary table, again, very much like standard Design Explorer, you can load results. In this case, we have two types of results because we're generating topology or generating concepts. So you can load an element density result and interrogate that, drill down as you would with a typical topology optimization, or you can load the simulation results that come along with it. So you can besides looking at the concept and looking at the design, you can also verify or validate the simulation results. So like stress, contours, displacement, what have you. Brand new to the generative design workflow is alongside the summary tab, we have what we call a preview tab now, where you can preview all the concepts or all the designs side by side or in a matrix. And I'll show you all this after summarizing it. But you can view all the designs or all the concepts, next to each other, for visual inspection. And there's some nice new filtering tools that you can filter based on the different variables that have gone into the concept generation. Again, I'll show this in a demonstration so it'll become clearer. We have incorporated, as we try and do everywhere we can in Design Explorer, machine learning and artificial intelligence. In this case, besides being able to, as was shown in the previous bubble, being able to view and visualize and filter according to attributes. So attributes, we'll look at these, but could be things like which types of symmetry were used, which draw direction, minimum member size, things like that. You can filter based on. But in addition, when we've generated all these different concepts, as you'll see, we may have lots of concepts that look similar or appear like one another, and you have just this kind of a whole matrix of them. We use the ML and AI to automatically group these according to what we call concept families or design concept families. So it kind of tries to group the designs together. So if there are many that are very similar, you don't have to go through one by one. We can group them into families, and then you can look at one family or another to help your down selection or your selection of designs of choice. And then the final thing I wanted to point out is we're leveraging a design space tool, the shrink wrap tool that is part of the design space or concept tools. And we're leveraging that. Once you've chosen a design or two that are of interest, we leverage this shrink wrap feature to let you generate an initial mesh from your design that could be used. You could hand this back to the design team to generate CAD, or you could try and use this to do some different prototyping or simulations based on a concept of choice. So this is just another look at the part family or the clustering concept family tools that I mentioned. So what's depicted here from left to right is it's a high level view of the workflow. So you do your design space creation to set up your design space. You run your generative design, and you generate in the second column there potentially all these different, I think there's 35 to 40 different concepts that were generated in this example. And then you can use the different tools again to view the results, to filter and to try and interrogate and look for maybe designs of interest. In the third column, using our AI or the clustering technology, we group these into different concept families. And again, it's just to help you to be able to visualize different concepts together or individually, and then ultimately down select your potential final design. So this slide I wanted to give just a little bit kind of deeper into what's going on in this workflow, and some of the benefits or how it compares to maybe a typical sort of ideation or topology optimization or concept kind of workflow. And along the top, just using the same example again, this example happens to be a bracket on a Chevy Silverado frame or chassis. But a typical sort of process might be setting up a topology optimization from creating your design space and setting up your optimization is kind of shown in the first red arrow. So there's some time and effort involved in that. Then you run a topology simulation, and you get some results, or you get a result. You get a topology. You may spend some time to change some parameters of your design, maybe or of your topology optimization. Maybe you want to try a different draw direction, or you want to explore some different symmetries, or change a material, what have you. So you'll spend some time, you'll set that up, you'll run another topology optimization, you'll get a different result, and so on and so forth. And that's what's depicted across the top. And in this example, we generated 11 different variants based on changing some of the aspects of the topology optimization. In this case, took about an hour to do all this, and we got 11 different options. And it's not I won't say it's a random process. I mean, you make engineering decisions based on changing different attributes and getting different results, but it's somewhat uncontrolled, and it's also somewhat labor intensive and somewhat time consuming to generate these designs. Also, you may or may not have the pedigree that you maintain pedigree. You might not know what attributes changed within one design to another, and you might lose track of that. So all those things, and probably many others, can be encapsulated into this generative design workflow shown on the bottom. And in this case, it's a single setup. You set up your topology optimization one time, you define your design variables that we'll talk about in a second. What are the aspects of the topology optimization you want to allow to vary? And then you click go, basically. And in this case, for this example, we got 37 different concepts to explore in about the same amount of time, maybe even just slightly less time, but in about an hour. Again, we generated all these different concepts. You then have the single setup You generate a lot more data, a lot more efficiently, and we can cover, again, there's a design space implied here based on the attributes and things that you're changing. We can more efficiently and more completely cover that design space. You can try more things. You can get more results in a shorter amount of time. And then again, we maintain the pedigree. So for each and every one of those potential concepts, you know what it consists of. This was this draw direction, this symmetry was used, this material, this minimum member size, and so on. And in fact, what you'll find, or what I think one can find, is that like any optimization, topology optimization, you can set up a problem and you say, I want to consider, this set of attributes, and you get one set of topology as an output. If you change those parameters, maybe some of them even subtly, you might get a very different concept. So in other words, the output can be somewhat sensitive, or maybe more than somewhat, can be quite sensitive potentially to the various inputs that you give it. And if you go off in one direction, you might get one concept or one set of types of concepts. But if you allow Design Explorer and generative design to have at it, so to speak, then again, you might get many different concepts, and some that you may not have considered otherwise. So finally, before I do just jump in and kind of demonstrate the workflow for everyone, kind of peeling back the layers one step further, essentially what we're doing here, just for everyone's information, is we're running a design of experiments, which Design Explorer is already good at. But in this case, each and every run in the DOE is itself a topology optimization. So that's kind of what I've already described. So as such, we vary the parameters of the topology optimization based on user input, and then allow the different topology optimizations to run, and we can get a set of potentially very different and many different potential concepts. So this is just a quick look before we jump in at the design variables that are currently supported. As with Design Explorer, anytime we create a design variable, we're just basically parameterizing an attribute on an entity. So for example, in a very basic example for Design Explorer, just generally, if you have a part thickness and you want to let that vary in a design of experiments or in an optimization, we're manipulating or parameterizing and then manipulating the thickness on a P shell or a section shell or whichever card holds the thickness in that case. So this is really no different. In this case, the user will have set up a baseline topology optimization. So they'll have defined the topology design variable, the DTPL and OptiStruct, and there are many attributes on that card, for example, and we're just allowing you to vary them or parameterize them in effect. So for example, the first three there, draw, stamp thickness, and symmetry, just pointing out where those are on the DTPL. So if you set up a single topology optimization, you can specify a draw type. You can have no draw specified, or you can have a single draw in a given direction. Well, we let you sort of play with that and say, I want to consider no draw, or I want to consider draw in the X, Y, Z, or custom direction of your choice. And I want to consider any of those to be feasible within my concept or within my topology optimization. We do the same thing for stamp thickness. Do you want to consider stamp designs or not? And you can consider both at this, stamped and non-stamped at the same time. Do you want to consider different symmetries? Again, if you're setting up an individual or a single topology optimization, you might define, as shown here, like a one plane symmetry in a given direction along, X direction, Y, or a custom direction. And we do the same thing that we do with the draw. If you want to consider symmetry in one direction or two or many different directions, you can consider them all. So this slide is just showing, and I'll leave this for reference, but it's just depicting which parameters or what is being parameterized when the design variables are created. And this is the set things that we can currently allow you to vary or to consider within your generative design. And it's a pretty decent set, I think, but there are more things on the DTPL, and there are more attributes that maybe we want to consider in the future, and that, so we'll have to continue to evolve this solution as we go. So this is a video of the demonstration. I'm going to jump and do a live demo right now. I just think it'll be hopefully a little more interesting, a little more interactive. So let's jump right into the demo now. And this is the same example that was described in the slides and is shown in the video that I just mentioned. This is a portion of that Silverado chassis. And there is, as you can see, the problem here is coming up with a design for this mounting bracket on the back of the frame. So just as a lead into this, the user would have created a baseline topology optimization. So they would have created the design space as is seen there. Just as an interesting aside, to create this design space, the AutoBox feature here from the design space ribbon was used. It's not part of Design Explorer. It's part of the design space tools. So it's not really in scope for this demonstration. It would have been done beforehand, but I just wanted to mention it. If you're not familiar with it, it's a really nice, handy tool for creating the volume that we've done here. So it's worth checking out as well. And if you're going to look into, it's worth checking out on its own, but certainly for generative design, it's been very handy as well. So I just wanted to give that a mention. But in this case, and I'll just let me jump to the model browser. You can see there's one design variable. That's that DTPL that's here. So again, the user would have set this up with whatever parameters they want to consider for their initial topology optimization. And everything is set up for OptiStruct to run topology optimization. There's an objective, I've got constraints, and there's a couple responses that are previously defined. So that's kind of the user's responsibility leading up to generative design. Just as with any exploration in Design Explorer, we typically start with a running simulation. So this is really no different in that sense. Okay, so jumping to the Design Explorer part, so that's all set up and ready to go. Now we're going to jump to the Design Explorer and we'll look at how we would set up, run, and then evaluate or look at the results from generative design. So everything is here. So this is the standard Design Explorer ribbon I've got open. We're going to come to create an exploration. And in this case, you can see we have a new generative design exploration type that's available in 2024. I'm going to click that in a second. I just want everyone, if you would, just kind of watch the ribbon as I do it. I can go back and forth, but just once I create a generative design exploration, the ribbon is going to change. So, and if there were other explorations in this session, so if there was another DOE or another optimization, based on which exploration is active, the ribbon will dynamically, automatically update. So in this case, because I'm doing generative design, and that's my active exploration, I get the list of design variables that we just looked at on the slide that are relevant to generative design. And if you're doing a different type of exploration, a DOE or an optimization, then you would see the standard set and back and forth. We've also filtered out a couple responses that are maybe not relevant for generative design. And then another thing that you'll notice here quickly is when the generative design exploration is created, we automatically include any DRESPs or OptiStruct topology optimization responses that were there in the topology optimization. We add those automatically as responses for our generative design exploration. So I can just click and activate those if I want to just use the same ones. Now I don't need to create any new responses if I don't want to. Okay, so we'll create the design variables now that we want to include in this generative design. So just the ones that I mean, we'll just go through. So draw direction. So in the case of draw direction, we can add any draw directions that we're interested in. We can say we want to consider designs with no draw direction. We want to consider X, Y, and Z standard directions, or we can add custom directions based on clicking on this add row, and then we get these planes here, and then you can pick any draw direction that you like. You know, you can use the plane and the manipulators and say I want to create one that's, you know, whatever, 15 degrees about whichever plane that is, and create that, and I can rename it C15 or whatever. So I can create any number of different draw directions that I want to consider, say okay, then I get that design variable created. Let me jump to symmetry, because symmetry works in the same way. So I can consider, again, maybe no symmetry. You know, don't consider symmetry, just let the design evolve as it will. I can remove that one, or again, I can consider X, Y, Z, or I can define custom planes of symmetry, just like the draw direction. Remove ones I don't want, and so on. Say okay, and I get the The symmetry design variable pattern grouping, that's the attribute on the DTPL that's being manipulated for the symmetry. Stamp thickness, if I want to consider stamped or non-stamped designs together, then I can create stamp thickness variable. This is a discrete variable always, and I can just add rows, define again on that DTPL card, what is my blank thickness that I want to consider. So maybe I want to consider a blank thickness of 3 millimeters. Maybe I want to consider also one of 5 and let it consider any of those. We'll create that one. The rest kind of work the same, and they all work, for everyone who's looked at Design Explorer before, they work just like Design Explorer tends to work. So if I want to have a minimum dimension, I can click on thickness constraint, and then I have all the options available to me. By default, if there's a minimum dimension on the DTPL, in this case, I think it's 10, I don't remember. But then I can let that minimum dimension value vary. Again, as with any Design Explorer variable, plus or minus 10% of its default value. I can enter a discrete list. I only want to consider minimum dimensions of 5, 10, 20, 30, or I want to explicitly define lower and upper bounds for my minimum dimension. Similarly, I can create stress constraints. If there's a stress constraint on the in the topology optimization, I can say, well, maybe the stress constraint default was 200 megapascals. I want to relax that or let that vary between 150 and 250 and see what different designs I might get. I can choose different materials. If I want to consider designs made from different material types that are in the model, I can select those, and then again, within the design of experiments, within the generative design output, it will consider designs. Basically, as I said, it's creating a DOE, so it's going to vary the combinations of all these different parameters that I give it, and generate all these different concepts. So at that point, maybe I've set up my my generative design workflow. Come to the evaluate button. Again, standard Design Explorer. In this case, based on running a MELS DOE with the given inputs, it's proposing 21 runs by default. I can change that value, generate more concepts or less if I'm in a hurry, and go ahead and execute this this exploration. One thing to note is just like the extended DOE feature that I mentioned at the beginning, that's available here too. Once this is run, if I want to see more designs within the same space, I can just right click on the generative design, in this case DOE, and I can generate more concepts. So I essentially extend that DOE. So let's go ahead and let's look at the results from a previously run example, or the same example, but one that I had previously run. Okay, so loading this one, and you can see it's been set up much like what I was just walking through. So we have a draw direction. We're considering stamping designs. We have some symmetry defined, and we have a minimum dimension that we use as a design variable. So once this has run, we can open Results Explorer, and let's just take a look at some of the tools that are available once I've generated, because I think this is where the interesting stuff is. The setup is fine and good, but once we've done the setup and we've generated designs, what do we get? So we get the summary table, as I mentioned in the slides. I can hover over my baseline run or any of the different runs in the table, and I can see what what the concept looks like for that given run. And you can see in the table again just an overview of the attributes that make up that particular design. So the one that we're just happen to be hovering over here has no draw direction. It's got a symmetry about the X plane, and it's non-stamped clearly, and has a minimum dimension of 20. I can right click and then I can load results. So let's just load. You can load the simulation results, or you can load the element density results. Let's load those. Look at those here, and then I can just come in here. Again, this is just an individual topology optimization that's been run. So maybe I want to look at the ISO plot for the element density and take a look at that and say, well, okay, that looks interesting. Maybe that's a design I would like to consider. But before we do that, let's go over to the preview tab and take a look at that. Let me add some space here. Okay, so the preview tab has some features here that I described. We get a table or a matrix here of all the different concepts that were generated by this generative design exploration. Excuse me. I have some filtering tools at the left, so maybe I just want to see only certain filter certain designs or certain concepts with different draw or symmetry, or maybe I just want to look at non-stamp designs, so I can sort of down select from there. If I click on any given design or any concept, any run, then at the bottom, the table, essentially the entity editor, updates, showing me the characteristics or the attributes of the selected design. So I can see let me just click on run 5 again. We'll just keep using that one. Again, no draw direction, X symmetry, and so on. I can click on, maybe I have one or more designs that are of interest. So maybe, I don't know, click a few of these, click one down here. So I can click any number there, and you see the compare button is highlighted here, or is capturing the number that I've selected. I can click on compare, and then it'll load the designs that I've selected side by side together. So I can again look at maybe I want to interrogate these a little more deeply, or side by side, I want to look at the element density and so on. I can do that. One of the other features that's here that I mentioned is this. So right now I'm filtering by variables. You can just kind of click on the little trash can here or deselect to update your filter. Besides that, I can sort or filter by concepts. And this is the AI tools that I was mentioning. So it's generating the clustering right now. And it'll group these into concept families. I can change the families. And now if I click on any part family or concept family, it shows me not the attributes of an individual one, but it shows me which concepts or which runs in my exploration are part of this particular family. So again, it's helping me kind of down select. It's grouping these it's clustering based on element density, basically, is what it's doing. So it's helping me kind of down select. If I have one or more, I can click on, again, to compare. We'll just click on one. But if I want to compare the concepts in this family, I can click that, and now it opens. And if I can animate through this either quickly or just step by step, and it's just showing me all the designs in this particular family. And at the top, you can see this is run 11. If I click next, it's run 16, and so on. It's corresponding to the runs that you can see in the table here. So I can just kind of step through these either quickly or individually, and again, help me to down select based on a particular concept family is the gist of it. And the last thing, so let's say then I've kind of done my interrogation. I can use these tools to interrogate, to down select, to look at results. Once I found one, maybe in this case it's I'll just stick with design 5, which is the one that's open here. But once I found one that is of interest to me, the last thing I want to show is I can right click and this wrap design. And here we're leveraging another one of the tools that's in the design space tools, or the concept tools, the shrink wrap. So we're kind of leveraging that. And if I click that, again, it's prompting me with some of the information necessary to generate the shrink wrap. And maybe based on my element density isoplot here, I know I kind of want to consider a minimum element density of 0.7, which is, I think, what's shown here. We'll accept the rest of the defaults, and we'll click Mesh. And then down in the lower right-hand corner, it opens a new HyperMesh window, and it generates, using the shrink wrap tools, it generates this shrink wrapped mesh that I could then use again. Like I can send this back to maybe to a designer to create some geometry for me or whatever. But I think that's kind of another handy next step in taking my concept and kind of getting it prototyped or used. I think that's the update. So thank you.